Hello, so today we're going to be looking at mutually exclusive events in probability. So what are mutually exclusive events? These are events which cannot occur at the same time. For example, it's impossible to turn left and the right side at the same time. Of course, you can turn left and then turn right, but you can't do it at the same time. Or for example, you can't win and lose at the same time. So those two events can't occur at the same time. You can't say you've won and you've lost at the same time. However, for example, in a tournament, you could win some matches and lose some matches, but of course, at the end of the day, we did one winner, so you can't win and lose at the same time. Now, for mutually exclusive events, the probability of A intersection B is 0 because these events cannot occur together. So the probability of A union B is, remember, initial probability of A union B is equals to probability of A plus the probability of B minus probability of A intersection B. However, for mutually exclusive events, this is 0. So that means the probability of A union B is the same as probability of A plus the probability of B. So of course, sometimes you can even be asked to prove that the following events are mutually exclusive, and what is required of you is to show that for any events that are mutually exclusive, when you get a probability of A union B, it will be equals to the probability of A plus the probability of B. Now for Venn diagrams relating to mutually exclusive events, A and B, they are like this: probability of A, probability of B. You see there is no intersection. Now still the probability of A union B complement is still here. So this is, and everything still here adds to 1. The only difference is there is no intersection. Now here we have a question saying mutually exclusive events A and B are such that probability of A is that, probability of B is that, find A union B. Now A union B, I think now this should be obvious. A union B is going to be equals probability of A plus the probability of B. So this is going to be 0.3 plus 0.6. Now another thing you should note, for this question here, we have been told that these events are mutually exclusive by the examiner. However, there's a type of question where you're not told that these events are mutually exclusive and you're required to just think about it and realize. However, it requires deep thought because in some occasions you can actually think events are mutually exclusive when they are not. Let me give an example. If I'm throwing if I throw a coin, I toss a coin, the probability of getting a head, you can't get a head and a tail at the same time in one throw. Like if I throw a coin, I toss a coin, you can't get a head and a tail at the same time. However, when you toss this coin consequentially, I toss a coin, then I toss again, it's possible that on the first throw I get a head, on the second throw I get a tail, on the third throw I get a head again. So that's a different thing because you're throwing it many times. However, in one single toss, you can't get both head and tail. Same thing. So we are going to deal with events where you're having very many throws or very many, so you should be able to follow and understand when the concept applies and when it doesn't. So find the probability of A intersection. So for those who haven't watched the first section, we said when you have that, you draw this small thing to remind you it's probability of A, probability of B. You shade A complement like this. Everything outside A, that's what A complement means. You shade B complement. B complement means everything outside B. Now, since the question wants intersection where these two meet, and you can see they meet in the outside. So what does that mean? It's the same as probability of A union B complement. It's the same as 1 minus probability of A union B. 1 minus 0.9. Answer is 0.1. However, with enough practice, it actually becomes really obvious that this is equal to that. But it's still okay. For now, you can actually always. Then a probability of A intersection B complement. Now, I think in the future I'll introduce us to a contingency table, but for now we know that probability of A is the same as probability of A minus probability of A intersection B. And here we have 0.3 minus 0. So the answer here is this is 0.3. So I hope this makes sense. Then now moving on to this probability of A union B complement. Now I told you don't have to cram this, you just come and draw your diagram here. So actually the basic rules of probability keep applying whether we are dealing with mutually exclusive or independent events. What changes is the key concept for that type of event. So probability of A, shade A, then B complement, shade B complement. B complement means everything outside B. So what I'm just trying to say is that you don't have to cram that when I have this union, this complement is this, you don't have to cram, you just, so now you see here we have this, when I shade everything outside, set B, and I shade everything in, now the question wants union, that means everything that has been shaded is needed in this question. So here, this means probability of A union B complement is the same as probability of A intersection B complement the complement. And now for the case of these events, by the way, we should have just drawn this, but sorry, we should just draw something like this, probability of A, since these are already mutually exclusive events. So we'll shade this as A and shade everything here as B complement. So you get this the same as saying this is B complement. So this is 1 minus probability of B is 0.6. Answer here is 0.4. That's probability of A union B complement. Then I have probability of A complement union B complement. So here I told you the same thing, you just draw very fast, shade A complement, this is A complement, you shade B complement, this is B complement. So I think here you realize when you shade, everything has been shaded. So because we have A complement everything outside A, B complement everything outside B. So you realize that when the quadrant needed for this question is actually everything, because A complement is everything outside A, B complement is everything outside B. So you realize at the end of the day you've shaded everything. So for this case, since they want union, so everything that has been shaded, and of course this would be 1. So but however this would be a different thing if this weren't mutually exclusive events. Hope you get the idea. So now let's move on. So here we have a question saying probability of A is 1 out of 5, and the probability of, okay, now for this we have events A and B are such that probability of A is this, probability of B is this. Find the probability of A union B when A and B are mutually exclusive events. So we are actually going to do this one. So when A and B are mutually exclusive, of course, you know, for mutually exclusive events, probability of A plus probability of B, would have said minus the intersection, but it's 0. So we just add 1 out of 5 plus 3 out of 4. And here you get this is equals to 19 out of 20. And the second part says find when probability of A intersection B is equals to 1 out of 8. So here I would say probability of A plus the probability of B minus probability of A intersection B. So you would say this is 1 out of 5 plus 3 out of 4 minus 1 out of 8. So see, this is actually 33 out of 40. Okay, so now let's move on. So here the question says events A and B are such that probability, so I think here this equals, then probability of B is a half, and then that of A complement intersection B is a half, state with a reason the relationship between A and B. Now for this question we have to look at what we've been given, the probability of A, probability of B, and then the probability of A complement intersection B. Now I think these are the only two that so far we can use in a proper relationship. Now of course when you're doing this question you don't know that here sadly we already know you're talking about mutually exclusive events, but when you're given this number you don't know what to think of. So you, let's say maybe draw this. So However, now for us we are somehow biased because you already know the video is on mutually exclusive events, so you would not try, you would actually just draw this. So that's why I've said you first draw this, then you now come and fill in. Now you have A complement intersection B. This is here, half. So I think you can already see the relationship. This a half and this a half. So that means this is 0 because probability of A complement intersection B is supposed to be probability of B minus probability of A intersection B. But now for this case, this one and this one are equal, so that means this is 0. So the relationship you would state events A and B are mutually exclusive events. Then you state because these and these are equal. The probability of A complement intersection and the probability of this are equal. Now the question wants you to find probability of A complement intersection B. Now for that, I think let's now draw because we already know probability of A is third, probability of B is half. So when you look at this, now for this, we already did this. I told you with practice, you can easily know that when you have this, it's the same as probability of A union B complement, meaning I can just find the probability of A union B, then I get its complement. So here I have third plus half, third plus half. I have this is 5 out of 6. Probability of A union B is 5 out of 6. The probability of this would be 1 minus 5 out of 6. This is 1 out of 6. Probability of A complement intersection B complement is 1 out of 6. So you see, just like that, we can solve this question. Okay, so let's now, in a soccer competition, the probabilities of team P, Q, and R winning the competition are this, this, and this respectively. So now for this question, we have actually 3. But as I told you, now for this question, it's not written anywhere that these are mutually exclusive events. It's just supposed to think about it and realize that these teams winning this competition these teams winning this competition are mutually exclusive. Not all of them can win the competition at once. So the probability of team P winning is a quarter. Probability of team Q winning is 1 out of 8. Probability of team R winning is 1 out of 10. So these are probabilities. Now the question wants team P or Q wins. Now remember we said or means union. So when they say probability that team P or Q wins, the same as probability of P union Q. So this will be the same as probability of P plus probability of Q, because you've found out that these are mutually exclusive events. However, now someone who hasn't figured this out would have already drawn this. We have a video on a 3-Venn diagram, but that's a different concept. So someone would have already drawn this and started working it out as this, and the question would become really complicated. But now you see, for this is actually simple because you just have this to add this, and you'd have this is a quarter plus 1 out of 8. Quarter plus 1 out of 8 would get 3 out of 8. So it's probability of P or Q winning. Then the probability that none of these teams win, so that's probability of P union Q union R. So here we have, complement. So this is 1 minus probability of P union Q union R. So the only way you would have figured this out is by thinking through these events and realizing that these are actually mutually exclusive events and they can't occur together. So meaning if we were to draw the diagram, it's something like this. P, Q, R. So probability of P plus probability of P, okay, plus R. So we'd have Q is 1 out of 8 plus P is a quarter plus 1 out of 10. and here I would get 19 out of 40. But we wanted the complement, so this probability of P union Q union R complement would be 1 minus 19 out of 40, and would get 21 out of 40. Then at this part, neither team Q nor R, so you're supposed to get probability of P Q union R complement. So this would be 1 minus probability of Q union R. So get probability of Q union R. Since these are mutually exclusive, now this would actually be very wrong if you're dealing with a normal three Venn diagram question. So three-state Venn diagram. Now you should actually watch the video on the three-state Venn diagram to have proper context, because this would actually be very wrong for you to do if these were not mutually exclusive events. This would be P plus Q plus R, and that would be 1 out of 8 plus 1 out of 10. So 1 out of 8 plus 1 out of 10. So you get 19 out of 40, sorry, 9 out of 40. Subtract 1, you get 31 out of 40. So that's the probability that neither Q nor R wins. Moving on, now a card is drawn from an ordinary pack of 52 playing cards. Find the probability that, now this is the same thing. I told you that if you to draw successive draws like I'm drawing, first time, second time, third time, that is not, actually that's now like a mixture, because at each of the events you're having mutually exclusive, but however in the long run you're not having mutually exclusive because there are very many events occurring. But now in this case I'm just drawing one card from an ordinary pack of 52 playing cards, and we explained how these cards appear in the, I think, the first or the second video in probability. So the question is saying find the probability that a card drawn is club or a diamond, or in probability means union. Probability of a club plus probability of diamond. So we said there are 13 clubs, there are 13 diamonds. And there are 52 playing cards. So here we have a half. So hope you see I've not subtracted minus probability of C intersection, the over club intersection diamond, because in one pick I can't pick any card like where there's an intersection, because these are mutually exclusive. So I hope you see the concept of mutually exclusive in this, that no one could have to tell you that these are mutually exclusive events. So here they said probability of a club or king. So a club, there are 13 clubs, because probability of club plus probability of a king. So you can't subtract because okay, now in this part, okay, so for context I think I may have to re-explain the concept, because so we have this, we have the heart, we have a diamond, we have a flower. So these are the four different cards we have. So this one is red, pink, this is red, this is black, this is black. Now we have, for each of these colors we're going to have numbers from 1, 2, 3. Actually we are going to start from A, 2, 3, 4, 5, 6, 7, 8. Okay, so 8, 8, 9, 10. Then you have the J, a Q, and a king. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So each of these has 13. So we have 13 diamonds, 13 spades, 13 hearts, and 13 flowers. Now we are going to have a king from diamond, a king from this, a king from this, and a king from this, like same thing with all the others. Now the probability of drawing a club, this is a club. Probability of drawing a club, there are 13 clubs, so it will be 13 out of 52. The probability of drawing a king, there are 4 kings because there's a king in each, so out plus 4 out of 52. Now for this case, actually this is not mutually exclusive, this is because we can draw a club who is also, we can draw a card that's a club and also a king, so that's 1 out of 52. I don't know if this makes sense. For this specific part, this is not mutually exclusive because here you can draw a club and a king, a card that's both a club and a king. So for that case, this will be 13 plus 4 minus 1. So we have this is 16 out of 52. So I hope this makes sense. So now for this question, you would have to interpret each part on its own, because so we now have a probability of a king or a queen. Probability of a king or a queen, you have to now think. So probability of a king, you can draw a king plus probability of a queen, but you can't draw a king and a queen at the same time. So these are mutually exclusive. Probability of drawing a king is 4 out of 52. Probability of drawing a queen is 4 out of 52. So I hope this is now making sense. This is 8 out of 52. Remember, in probability, you can reduce. I'm doing this off here. You can reduce this depending on the answer your calculator gives you. Probability of a heart, union, and ace. Oh, sorry, this is a club. Then this is the ace. Now, probability of a heart or an ace, heart plus ace. You can't draw a heart and an ace at the same time. So these are mutually exclusive. So probability of a heart, because there are how many hearts, there would be 13 hearts. So 13 out of 52 plus how many aces, 13 to 52 aces. So this gives you a half. So hope this makes sense. So what does this number show us? This number shows you that you should actually be thinking about the concept of what are mutually exclusive events. Are these events mutually exclusive? So if you keep thinking of it in real time, it's going to make sense. Alright, so thank you for come to the end of the session on mutually exclusive events. So I think now we're going to move to the next kind of events. However, there will be an exercise that will have more numbers, more practice on this same concept.